This is chapter 6 of Logic and Computer Design Fundamentals. And today we will focus on the part 2 of the sequential circuit, which is sequential circuit design. In part 1, we went through the types of sequential circuits, storage element, and the sequential circuit analysis. In part 2, as we said, we will focus on the design part. The design go through a systematic steps, starting from specification, and then formulation, and then state assignment, and then flip-flop input and output equation determination, the optimization, and end up with verification. Those steps are called the design procedure. We will check each one of them by explaining the steps using examples. The specification usually using English language. The formulation is obtaining a state diagram or state table from the specification. The state assignment, we assign binary codes to the states. The step of flip-flop input equation determination from the state diagram or the state table, and after assigning the states with codes, we select flip-flop types and derive flip-flop equations from the next state inference. The output equation determination, we do the same thing, but for the output. For the optimization stage, we optimize the equation. We already discussed the Carnot map, and we will use K-map usually if the number of inputs and the number of states are limited. Technology mapping, we find a circuit from equations and map to flip-flops and gate technology. So based on your choice, based on your choice of gates, you build up your logic equations. In the verification stage, we verify the correctness of the final design. The specification is usually written description or mathematical description using hardware description languages like HDL and Verilog. It uses tabular description, some of them, like the truth table, or an equation description, or a diagram describing the operation. That is not the structure. The formulation step, the job is to find the state diagram. A state is an abstraction of the history of the past applied inputs to the circuit, including the power-up reset of the system reset. The interpretation of the past input is tied to the synchronous operation of the circuit, meaning an input value other than the asynchronous reset is measured only during the setup hold time interval for an edge triggered flip-flop. At the end, we denote a state by a circle, and we write the name of the state inside the circle. Here are some examples. State A represents the fact that a 1 or a logic 1 input has occurred among the past inputs. State B represents the fact that a 0 followed by a 1 have occurred as the most recent past two inputs, and so on. In specifying a circuit, we use states to remember meaningful properties of past input sequence to serve our needs to convert the specification to state diagram. These past input sequences are essential to predicting the future output values. As an example, actually a well-known example, a sequence recognizer. It is a sequential circuit that produces a distinct output value whenever a prescribed pattern of input symbols occurs in a sequence. Meaning, it recognizes an input sequence occurrence. Do we have a 1 in the past? Do we have a 0 followed by 1 in the past? And so on. We will develop a procedure specific to the sequence recognizer example to convert a problem statement into a state diagram. Once we come up with a state diagram, the state diagram will be converted to a state table, and from that we will continue the design steps. The sequence recognizer procedure are listed here in this slide. To develop a sequence recognizer state diagram, you begin in an initial state in which none of the initial portion of the sequence has occurred. Typically, it is called the reset state. And then we build up the state diagram by adding a state that recognizes that the first sample has occurred. The sample being the value of 0 or logic 0 or the value of logic 1. We add state that recognize each successive sample occurrence. The final states represent the input sequence, possibly less than the final input value occurs. And then we add the state transition arcs, which specify what happens when a sample not in the proper sequence has occurred. So we basically first go through the sequence or the wanted sequence, and then we check what happens if the sequence doesn't happen. What should we do? And then we add other arcs on the non-sequence input, which transition to state that represent the input subsequent that has occurred. The last step is required because the circuit must recognize the input sequence regardless of where it occurs within the overall sequence applied since the starting reset. To explain those steps slowly, we will have a sequence, an example sequence, and we will try to recognize this sequence step by step until we generate the state, the full state diagram. Now, to discuss the step of state assignment, you should know that each of the M states must be assigned a unique code. The minimum number of bits required, if we call it n, then this n is larger than or equal the ceiling of log m to the base of 2. There are useful state assignments that use more than the minimum number of bits. If you want the minimum, then it will be the lower bound, which is this one. And there are different state assignments that take more than that. If you specify the number of bits that you want, n, then there are 2 to the power of n minus m unused states. As examples, let's say that we are looking for the lower bound number of bits. So to find the minimum number of bits for 6 states where m is equal to 6, we plug this 6 here, and we find out that the equivalent of this part is 3, which means that n could be larger than or equal to 3. To get the minimum, it's going to be 3 bits. It's going to be 3 bits. Now we have 6 states, and we will use 3 bits to assign code for these 6 states. This means that we have 2 to the power of 3, which is equal to 8. 8 minus 6 is equal to 2 unused states. Since we have only 3 bits, I will write it down here. Let's say we have 6 states, and we will have 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1. So we have 6 states. Since we are using 3 bits, these are 3 bits, each one of those bits will be mapped to a flip-flop. So the number of flip-flops are the same as the number of bits. We will have in the final design 3 flip-flops only. Now, the 6 states are, for example, I will assign this code to the first state, this to the second, and so on. So we have 6 of them. And we are left with 2 of the states that are unused. If, as another example, if we have m is equal to 10 states, then after finding n, after finding the left-hand side of this inequality, I mean the right-hand side, this will be equivalent to 4. Therefore, we will use 4 bits, and we will end up with 6 unused states. So we have 10 states that are used, 6 that are not used. You can notice that if you add them together, 10 plus 6 is 16, and 16 is 2 to the power of 4. This is the example that we will go through. The example recognizes the sequence 1, 0, 1, 1. Note that the sequence, this one, contains this part here that we need to recognize. So it has this one, it has this sequence, and the beginning of the sequence, the 1, 1, is a proper, we call it a proper subsequence of the required sequence. This is the required sequence, and this one is called a subsequence. Thus, the sequential machine must remember that the first 2 1s have occurred as it's received, as it receives another sample. This tells us that this sequence, we will start having bits from the most significant bit position. So you will get the first one here, and then you will get the other one, and probably you think we are starting the sequence, but since you will get another one after that, which is not 0, then it's not the sequence. You cross it, and you try, and you keep trying, and you get the most significant bit first, and then the next bit, the next bit, the next bit, and the sequence recognizer, after it has the last 4 bits, it will tell you that the sequence has happened, and it will generate logic 1 in the output to tell you that the sequence happened. Also, the sequence, this one here, 1 0 1 1 0 0 1 1, it contains this part, and also it contains the other part that is here. As you can see, there is an overlap between the two sequences. So the moment you get 1, 1, and then 0, and then 1, that's a sequence. And then starting from this one, which is overlap between the two sequences, if you get 1 and then 0 and then 1, you will consider it another occurrence as well. So as we said, this sequence contains this part and also this part as both the initial subsequence and the final subsequence with some bit overlap, meaning this bit is overlap between the two. This one in the middle is the overlap, and the sequence 1011 must be recognized each time it occurs in the input sequence. So if you have this one, it will generate the output and make it 1, logic 1, 2 times, while this one, it will make the output equal to logic 1 only 1 time. So to build the state diagram for this problem, we will start building the finding the number of states required and building the state diagram, connecting the state using arcs and so on. So we define the state for the sequence to be recognized, assuming it starts with first sample and then continue through each sample in the sequence to be recognized. The output is 1 only when the full sequence has occurred. In this example, it's 4 bits. And the output is 0 in any other case. So we start in the initial state. Randomly, we name it state A. And then B is the state obtained when the input sequence is 1, which means that we got the first one. The transition arcs are used to denote what the current observed input is, which is this one. The input that we had is 1, and what the current resulting output is. If it is a Mealy model, then the output will be shown like this in the arc. The states are used, those states are used to name and to record the name and the code of the states. Right now, we are having the name of the state A and the state B, and tell us also what is the current resulting output only if it is a Moore model. We will build the recognizer of 1011 using Mealy mode and the Mealy model, and then we will convert it to Moore model in a later slide. So basically what happens here, state A is the initial state. We draw it. And then state B is the state that represents the fact that the first logic 1, or the first one, this one, in the input subsequence, subsequence has occurred. So if you are in state B, it means that we have already the first sample already have occurred in the past. This is the meaning of state B. Now, the output 0, this output being 0 on the arc from A to B means that the full recognized sequence has not yet occurred. Of course, we just started, we had only the first sample, 1. So the output is going to be 0. It's going to be 1 only when the whole sequence happens. And then we continue building the state diagram. Note that we started with the sequence. We start building up the state with the going along with the sequence. Now, next, after the next sample, which is the logic 1 happens, so we already have this one since we already have the B state. Now, if the next one happens, we have the C state, this C state, which is the state obtained when the input sequence is 1 and 1, meaning that the state C means that you already in the past have 1 followed by 1. This is the meaning of state C. Now, again, the output 0 here in the arc from B to C means the sequence has not been recognized yet, because you only have part of it. Now we continue building the state diagram. After the next 0 happens, which is this one, we have D state. This state, we call it D, which is the state obtained when the input sequence 1, 1, 0 happened in the past, which is denoted here, 1 and then 1, followed by 0. Same thing, this 0 in the output means that the full sequence didn't happen yet. Now, after this, finally, we have another one. So this one means that we had the bits 1, 1, and then 0 in the past, and this one just happened. So what we do in the state diagram, we have 1 and 1 and 0 in the past. We add only an arc, and we say that the input 1 happens, and because the full sequence now is represented in the state diagram, the output of 1 on the arc from D means that the sequence has already been recognized fully, and we generate the 1 in the output right here. You can see that this is fairly easy. You just list the states. We have 4 bits, so we will have 4 states for now, and then we will have the sequence recorded here, 1, 1, and then 0, and then 1. The output is always 0, except when it's fully happened. Now, after this, you ask yourself, when we are at state D, to what state should the arc go? This arc cannot be floating. It has to start from a present state and end up with a next state. So which one should we go to? Also, don't forget that we are allowing the overlap. We are allowing the overlap. Not that D is the last state, but the output 1 occurs for the input applied in D. This is the case when a Mealy model is assumed. So if we are doing a Mealy model, this is the way we build it. Now, to answer this question and to find out where this arc goes after that, now we know that the final one in the recognized sequence, 1, 0, 1, 1, is a subsequence of this one, meaning that we are allowing the overlap. If we allow the overlap, if this sequence happened, and at the last step in this arc, we had a 1. This final one is overlapped between the first and the second sequence. And because of that, we will go to the state that represent to me that I already have 1 in the sequence. And we defined this state before, and we know that this is state B. I will define them again. State A means that you didn't receive anything yet. State B, it means that you received 1. The state C, it means that you received 1 followed by 1. And state D means that you received 1 followed by 1 followed by 0. And since this arc have a 1, this one means that you already received the first bit of the sequence, which is this one. And because of this, you will try to find what is the state that represents the same thing. We know that B means that you already have a 1 in the sequence. And this is why we remove this arc and we redraw it this way. And we write down the same input and output combination. Thus, the arc should go to the same state reached after a first one is observed in the sequence. Now, I write it again in the slide. The state have the following abstract meaning. A, no proper subsequence of the sequence has occurred yet. B, the subsequence 1 has occurred. C, the subsequence 1 and then followed by 1 has occurred. D, the subsequence 1 and then 1 and then 0 has occurred. And the 1/1 on the arc from the state D to B, which is this one, means that the last one has occurred, and thus the sequence is recognized and the output is logic 1. Now, the other arcs are added to each state for inputs not yet listed. You should ask, what are the arcs that were missing from this state diagram? We know that the number of inputs that we have is only one input, which is this one. So if you were in state A and you received the input equal to 1, you'll go to state B. But what about if you receive the input equals to 0? You have to find this arc. It starts from A, you know it starts from A, but where does it end to? Similarly for B, we know the 1, but we don't know what about when the input equal to 0. For C, we know what happens when the input is 0, but we don't know yet what happens when the input equals to 1. And similarly for the case D, we know it for 1, but we don't know it for 0. Since you have one input, if one of the inputs happens, you already draw the arc here. So we have 4 arcs in the state diagram currently, and we need to add 4 more arcs. To understand this in another way, for each state, there should be 2 arcs going out from it, because the number of inputs is 1, and 2 to the power of 1 is equal to 2. So there should be 2 arcs going out from A, 2 arcs going out from B, and so on. Currently, each state has only 1 arc going out from it, because we build it using the idea of recognizing this sequence. Now we do this easily as follows. The state transition arc must represent the fact that an input sequence has occurred. And for A, if you have 0 in the input, it means that the sequence didn't happen, nothing of the bits happens, and you go back to A again. Now, if you are in B and you were expecting a 1, like in B means that you already have a 1, and if a 0 happens, it means you messed up the sequence and you need to restart again from A. Now, if you are in the C, and you should be careful here, C means that you already have 1 and 1. If you received another 1, this means that at this point, it means that you have in the past 2 1s, which is the definition of the state C. So you go back to state C. For the D, if the D means that you already have 1, followed by 1, followed by 0. If you receive the 0, then this means that the sequence is messed up completely, and you can't start any new sequence starting from this bit or the bit before it. or even the bit before for that case, and you need to go back to the very beginning, starting from A. You notice that the blue arcs that we added here all have the output 0. Frankly, all the arcs should be equal to 0 except one arc, which will recognize the sequence. It will recognize the sequence. And this is the way we build up the state diagram. So what we did is we started from the specification of the problem, which is simply the English statement that we need to recognize this sequence 1011. And then we formulated using the state diagram. Note that the one arc from state C to state C, which is this one, implies that the state C means 2 or more ones have acted. Now, from the state diagram, we can fill the state table. We know that there are 4 states, and we have 1 input and 1 output. Since we have 4 states, you ask how many bits I need to distinguish between those 4 states, and the answer would be 2 bits, because 2 to the power of 2 is equal to 4, and this 2 is the number of bits. So we know that we need 2 flip-flops, we need 1 input and 1 output. For now, we will just focus on the number of states, 4 states, 1 input and 1 output, and we will choose the form with 4 rows, 1 for each current state. From state A, the 0 and 1 input transition has been filled in the table along with the output. So as you can see, we start with any arcs. We will start from A, and we choose to start with the blue arc. So it means that if the present state is A and the input is 0, then the next state, we will go back to A, and the output is going to be 0. Similarly, for the other arc, we will say that if the present state is A and the input is 1, then the next state is B and the output is 0. Notice that from the statement that we had before, that we have 1 input and 1 output, this means we have 1 bit here in the input and 1 bit here in the output. If there are more inputs or more outputs, they will be shown, the inputs will be shown before the backslash, and the output will be shown after the backslash. Now, we'll start filling the state table in a similar way for all the arcs. Now, notice how many arcs we have. If you count them, you will find that we have 8 different arcs. Each one of the arc is a row in the state table. So we have 8 rows. Now, we filled up the full table, as you can see here. Now, this is for the Mealy model. We explained at the beginning that we will use Mealy model, and you can check that in the Mealy model, the output is specified by knowing the present state and the input. Simply, if you look at the state diagram, If you found all the arcs have this follow or had this form, being the input followed by a slash followed by the output in all the arcs, then this is a Mealy model. Now, what if we want the Moore model? The Moore model for a sequence synchronizer usually has more states than the Mealy model. The outputs are marked on the states. So you take the outputs from all the arcs and you put them inside the states. As you can see here, the state A have the output 0, the B have the output 0, also the C and the D. And you can see here, none of the states have the output equal to 1. And none of the states A, B, C, and D. Outputs are marked on the states, and arcs show only the transitions when a certain input happens. Now, what happens in the Moore? We added this new state. This is the most critical information. A new state E with the output value of 1 is added, which is added, as you can see here. Now, from this E, first, this E we added after the state D. So when you are in state D and the last input sequence bit happens, notice that this is 1, followed by 1, followed by 0, and now it's followed by 1. The last one happens, you added the new state E, and you say that the output now is equal to 1. So you added this arc, and you added the circle, and inside the circle you have E, and the output is 1. From E, you have 2 inputs. As this is the same thing for all the states. Since we have 1 input, we need 2 arcs going out from E. Now, if the input is 0, then the arc goes to A, because the observed sequence is going to be this one, and 1 and 0, 1 followed by 0 is not part of the sequence. It's not the beginning of the sequence. So you need to go to the beginning from A. If the input is 1, then the sequence is this one, and you can see that this is the beginning of the sequence. Actually, there will be 2 bits already of the sequence, and this is why we go back to C, which means that 2 ones already happened. You can compare between the previous slide and this slide, and you see the addition of the 3 arcs here, this one, and this one, and this one. And of course, we take out this arc from that was going to the P. Now, for the state table, there is a saying says that there are more states in Moore model, which is in short, more is more. Just to remind you to remember that in Moore model, we have more states. Now we fill up the state table the same way as we described in the Mealy machine, but notice that now the output, it's tied to the present state, meaning if you are in state A, the output is 0. If you are in state B, the output is 0. State C and D, same thing, the output is 0. The output is only 1 when you are in state E. Now for the next states, you just fill up this column. For the next state, you just follow the arcs. For example, if you are in state E and the input is 0, you go to A. You are in state E, the input is 0, so you go back to A. If you are in state E and the input is 1, then you go to state C. If you are in state E and the input is 1, you go to state C. Now, at this point, we reached to the stage of the state assignment in the design procedure. So let's take this simple example where you have only 2 states, and you can check the conversion from this state table to the, from this state diagram to the state table, and also vice versa. If you have this state table, how to build the state diagram. If you were asked how many state assignments of codes with the minimum number of bits, since we have 2 states, it's going to be 2 factorials. So we have 2 ways to assign codes to A and B. Either we make A equal to 0 and B is equal to 1, or we make A equal to 1 and B equal to 0. Now the question is, does this make any difference if you choose this assignment or this assignment? And you can see, because the number of states are limited, there is no big difference, big difference, only there is an inversion from going from this state to from this state assignment to this state assignment. I should remind you again, by saying state assignment, it means that we are writing the codes for each state, whether they are in the present state or next state. We write their respective codes. Now, let's go back to our example, which was in Mealy model, the one that we built to recognize our sequence 1011. How many state assignments of codes with the minimum number of bits? Since we have 4 states, it's going to have 4 factorial different state assignments, which is 24. One of them, for example, we will assign A 0 0 and B 0 1 and C 1 1 and D the left offer, which is 1 0. And there are 23 more state assignments. One of them is the one that I said, and 23 more if you do the different permutations. Now we will try to do it for 2 different state assignments. We will try to build the logic diagram for this state diagram. We will try to build the logic block with the gates and flip-flops. And we will do it for 2 different state assignments to check if there are any difference between the state assignment or not. So what we did is we have an assignment that we picked randomly. We know that we have 4 states. And since we have 4 states, the number of bits n must be larger than or equal to log of the number of states, which is 4, to the base 2. And we take the ceiling. If you calculate this, you will find that n could be larger than or equal to 2. If we want the minimum number of bits, then it's going to be n equal to 2. This is the lower box, which means if you have 4 states, then the number of bits that you need are 2 to represent codes for each of the states. Also, you can think about it in another way, an easier way. This, you would say that I know that I have 4 states, and I will try to find the nearest power of 2. You know, you have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. You know 2 to the power of 0 is 2. 2 to the power of 1 is 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And since you have 4 states, then you need 2 bits. Now, we know that we need 2 bits to have codes for each one of them. The first one randomly, we picked it as 0, 0. B is 1, 0. C is 0, 1. And D is 1, 1. This is one of the state assignments. And we have 23 more different assignments, as we explained in the previous slide. Now, now we have 2 bits. The first bit is going to be a flip-flop, and the other bit is going to be another flip-flop. Now, after having this assignment, we code the full state table. Meaning, previously, I'm going back to the previous slide. We have A here, and here, and here, and also here and here. We take out the A, and we put, instead of the A, its code, which is 0, 0. So we put it here, 0, 0, and here, and here, and also here, and here as well. So that's for the A. We do the same thing for B, C, and D, each one for their associate code. So B is going to be 1, 0, the C is going to be 0, 1, and the D is going to be 1. And so on. Now you can see now the state table is showing the same expected bits that we studied in a previous video. So in X, you have 0, 1, 0, 1, 0, 1, 0, 1. In Y, 0, 0, 0, 1, 1, 0, 0, 1, 1, and so on. 4 zeros and 4 ones. Notice that we had the input and we call it X. The output, we call it Z. Now, the next state, we call it D0 and D1. And the present state, we call it randomly Y0 and Y1. We just denote it with a certain name. It's good to have a letter that represents all the present states, for example, Y everywhere, and each bit has its index 0 and 1 and so on. Now, we try to find what is the Boolean function for each of the columns that appears after the inputs. So we will try to find the Boolean function for the output, for the first flip-flop, and for the second flip-flop. Now, the flip-flop that we are going to use is the D flip-flop. In fact, I only explained D flip-flops to you up to this point. So we obtain the K-map for each one of them. For example, in the output, we fill it 0, 0, 0, 0, 0, 0, 0, 1. In D0, we fill it 0, 1, 0, 0, 1, 0, 0, 1. You can see it and check it here. Similarly, for D1, we fill it this way, 0, 0, 0, 1, 1, 1, and 0, 0. Now, you notice that the Z, you only, to optimize using K-map, is you will have only this single one by itself. For the D0, we have those 3 separated from each other. So each one of them will be alone. There is no adjacent one that you could you can include in a square together. Here we have those together, 2 ones together because they are adjacent, and this one alone by itself. And from these, you can find the Boolean equation. For D1, you will have this one would be D1, Y1 and Y0 bar. And from this one, we have y1 bar, y0 x. For D0, we have 3 terms. Each one of them will have 3 variables, and you can check them. And the last one, Z, we have only this one, which is y1, y0, x. y1, y0, x. If you check the gate input cost for this one, you would see that the number of literals are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and you add the terms to 17, the terms that we have 1, 2, 3, 4, and 5, so that you end up with 22. The gate input cost will be 22. We only consider the terms that have an operation. A single term, we don't consider it. We explained this before. Now, if we take another assignment, let's say that we take this assignment. The difference now is we followed the gray codes, meaning the change from A to B is only in a single bit. From B to C, it's only 1 bit, which is this one. From C to D, the change is only 1 bit, which is this one. And going back from D to A, there is only 1 bit change, which is from 1 to 0. This is actually will assign nicely in the K map. So if we do the same way and we filled up the codes by this new assignments, and from the codes we fill up the Carnot maps, and we started to do the optimization, you will notice that the Z is still the same. It has a single input. It has the same function. But for the D0, now we have 4 ones that are close to each other. And we can include them in a big square. And this function would be X. Instead of having 3 terms in the previous slides, each term with 3 variables, now we have only 1 term with 1 variable. For D1, you have those 2 together and those 2 together, and there will be 2 terms. Each term will have 2 variables. The input cost now is reduced from 22 to only 9. You can count 1, 2, 3, 4, 5, 6, 7, 8, and you have 1 more term to make it 9. So the cost is reduced by a great number because of the state assignment. So to answer the question, does it make a difference? The answer is yes. It makes a big difference. The state assignment makes a big difference in the circuit of the recognizer. Now, to draw it, now we will go to the next stage of the design procedure, which is the mapping the technology. So if you have those 3 functions that we reached in the previous slide, to draw it, you can see that we need 2 flip-flops since you have D0 and D1. These are the 2 flip-flops. This is D0 and this is D1. The next state for D0 was simply X. The next state for D1 is the 2 terms, 2 ands with an OR. This is the OR. The first one being Y0X, and the second one being Y0, Y1. So, for example, this one is Y1. You can see that this is Y1, and this one is Y0. So this one is this and this one here is X and Y0. Now for the Z, which is the output, it's Y1, Y0 bar and X. You notice that we took the Y0 bar from the Q bar of the second flip-flop, DZ, or from the first flip-flop, D0. And we take the Y1 directly from here, and the X, we got it from the inputs, as you can see. This is the initial circuit. Now, if you had the restriction of a certain gate because you have a certain map technology, then if you were said that you will use D flip-flops, good, we are using D flip-flops with resets. This is the reset. So we need to have a reset, and we plug it in an input. We call it a reset. And you need to have only NAND gates with up to 4 inputs and inverters. You can see in our design, we have ORA NAND. Since the map technology now, we use NAND gates, we need to convert this to NANDs. The NANDs that we have 2 inputs, 3 inputs, up to 4 inputs. To do this, we simply convert this one to NAND by having a bubble followed by an inverter. And it says that we can use NAND gates up to 4 inputs and also inverters. So this is allowed. This is also allowed. For this one, you have the bubbles like this. Will be a NAND. This is a NAND. This is also an inverted input OR, which is an inverted OR simply, and which is also a NAND, a 2-input NAND. And this diagram now would be like this, as you can see. And we reached to the final result that recognized the sequence 1, 0, and 1, and 1. So for this circuit to operate, you will first block this one, starting from the most significant, and then the one after that, the one after that, and then the one after that. After you block those 4 bits, the output will be 1, Z will be 1 only when you're done with inputting all the 4 bits. If you put a long sequence, for example, you have 1, 1, 1, and then 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, for example, then after you have this sequence, you will have the output is going to be 1. And you will try to find other sequence with the same thing. You won't find any for my example, my quick example. So you will have the output Z only 1 time for this long sequence, and you can try other sequence, and they will have different outputs. Now, after this point, we have a full example describing what we said in the previous slide, going through the design procedure from the specification to formulation, which is finding the state diagram, and then after that we find the state table, and from the state table we did the optimizations and to find the Boolean function. After the Boolean function, we build up the block diagram, and from the block diagram we check the technology mapping, and we end up with a NAND result. And then you can do a quick verification by inputting the X's or the inputs being the X and checking the output for verification. Now we will continue by having different state assignment. Now this is called 1 flip-flop per state, or 1 hot assignment. It's a different assignment. Example code for 4 states. If you have 4 different states, meaning you will have previously in 4 states we will use 2 bits. Now we will use the same number of states. If you have 4 states, you will use 4 bits. But you have a condition. You will, in each state, you have a single logic 1. And this is why it's called 1 hot. So in equation, you need to include only the variable that is 1 for the state. State code 1000 is represented in the equation by y0 instead of this one, which because all the codes with zeros or 2 or more ones have we will have them as don't care as the next state values. So the state or the code 0000 is not allowed. The code 0110, for example, it has two ones, it's not allowed. Only the codes with a single one is allowed, and we assign them to states. We assign 4 of them to states. Since we have 4 bits, we have 16 different state assignments. We choose 4 of them, and we are left over with 12 unused states. Now we have this example using one hot assignment. If you have 4 states, A, B, C, and D, and you want to assign them those codes, A being 1000, B being 0100, C being 0010, and D being 000 and 1. Now, that's the same example that we had before, but now we have 4 bits for each state. The present state have from Y0 to Y3. The next state has from D0 to D3. Now we write it down this way: when the input X is equal to 0, and when the input X is equal to 1, similarly for the output. Now, to find the equation, we could read it from the table directly by, for example, the output is being the easier one. We have 1 in the output. When the input is having, we check the output here from and against the present state and against the input. So what happens? The output is 1 only when the X is equal to 1, and we have Y3 equal to 1. The other function, for example, D3, you notice that D3, you look at those bits and those bits, you have 1 here in D3, and this one happens when you have X equal to 0, being X bar, and you have Y2. For D2, you can see that D2 is here. And there are 2 ones, this one and this one. The first one happens when you have X and Y1. And the second one here, when you have X and Y2. Of course, you can get X as a common factor, and you end up with Y1 or Y2. You could also use the simple ideas, some simple ideas of Boolean algebra, and you can convert this one to this part here, where you get the other y's that weren't presenting in the equation, which is Y0 and Y3, and you make it all bar this way. And we discussed this a long time ago when we talked about the min terms and max terms. For D1, we have 1 here and here. So this is going to be XY0 and XY3. For D0, which is these bits here, we have 3 ones. This one and this one and this one. And they are all when X is complemented, X bar, 1 time with Y0, 1 time with Y1, and 1 time with Y3, as you can see here. Or simply you can take this out and you put the remaining Y, which is Y2, all bar, as you can see here, and this you will get a shorter representation. If you calculate the gate input cost here, you will find that the cost is 15. if you compare this to the previous design that we have here, this design have the gate input cost of 9. Now, this is another example. If you were asked to design a sequential modulo 3 accumulator for 2 bits, meaning you add and then you calculate the module. The definition, modulo n adder, it's an adder that gives the result of the addition as the remainder of the sum divided by n. Meaning, if you have those two numbers, you add 2 plus 2, you find the result is equal to 4. Modulo 3 is going to be 1. Now, the accumulator, it's a circuit that accumulates the sum of its input operands over time. It adds each input operand to the stored sum and so on, beginning from the initial case. In the initial case, the sum is going to be 0. Now, the stored sum, since it's modulo 3, you would need only 2 bits. Also, we mentioned here that they are 2 bits. We have the inputs x0 and x1. We have the output z0 and z1. And we will have the saved states in y0 and y1, being the first D flip-flop and the second D flip-flop. So to do this example, we do it this way. Let's explain it in the state diagram first, and then we will move to the state table. So you are beginning at state A, and you want to add, as we said here, 2-bit operands. So what happens, you have the addition of 2 bits. If the result is 0, 0, this means that you will go back to the same state, A. So the state A means that the current result is 0, 0. Now, if you are in this state, 0, 0, and the number that you want to add it to this sum is 0 and 1, if you add those two modulo 3, the result is going to be 0, 1. So you go this way. Now, if you are here and the current input is 1, 0, so you add 1 and 1, the result is going to be 2, and you will move to state C. So now you know that the definition of the states. The state A being that the sum result is 0, 0. State B means that the sum result is 1, 0 or 1, and the state C, it means that the sum result is 0, 1 or 2. In decimal, this is going to be 0, this is going to be 1, and this is going to be 2. Now you can see that we don't have a 3 because we are using a modulo 3. So if you are in state C, which is 0, 1, and the next number is 1, 0, you add 2 to 1, it's going to become 3, but you are doing the modulo, so you'll go back to 0, because 3 modulo 3 equals to 0, and so on. So you can see from this states, you keep adding the numbers and generating the states in this direction. Now, let's see change the color and see the other direction. Now, if you were in state 0, 0, the sum being 0, and the next number is 0, 1, you add those two, you will end up with 2. If you are having the value 2, and the current number is 2, so 2 plus 2 is equal to 4. Modulo 3 is going to be 1. So you'll go to the state. If you are here, so the sum is 1, 0, and the new number is 0, 1. You add 1 and plus 2 is going to be 3. Modulo 3 is going to be 0, and you will go back here. In the cases when the number that you want to add is 0, you will end up with the same state. So if you start with 0, the current sum is 0, and the new number is 0, you will go back again. Similarly here, you'll go back again, and in C, you'll go back again. This is the state diagram. Now we will move from this to state table. And since we have only 3 states, we need 3 codes. We will use 2 bits. We know that 2 bits will give us 2 to the power of 4. This is going to be 2 to the power of 2, which is going to be 4. And this 4 is the number of states that we can represent using 2 bits. But we only need 3 of them. So we will have 1 code that are not used. What we did is we will assume that A is going to be 0, 0, B is going to be 1, 0, and C is going to be 0 and 1. The state 1, 1 is not going to be used. And we write them in the table in such a way it matches the kernel map. So you can see that this is 0, 0, 1, 0, 1, 1, 0, 1. Now, this is Y0 and Y1, which is the sum that was saved inside the flip-flops. For the inputs 0, 0, 1, 0, 1, 1, and 0, 1, this input never happens. And you can see the addition of, for example, 0, 0, and 0, 0 is the same 0, 0. The addition of 1, 0, and 0, 0 is 1, 0, and so on. Similarly, for the B, you can see that adding 0 to 1 is 1, 1 to 1 is 2, 3 to 1 is 3 actually is not considered. And you will have the 2 plus 1 is equal to 3, mod 3 is going to be 0, and so on. Or directly you get this from the state diagram. So let's take it for C, for example. For C, if you are in this state, 0, 1, and the input is 0, 0, this is the input 0, 0, you end up with C again, which is going to be 0, 1. If you have the other input 1, 0, you will go to 0, 0. If you have 0, 1, you will end up with 1, 0. Now, the outputs, since if you were asked what is the model that we used in this state diagram, you know that this is a Moore model because the outputs are associated with the states. This means that the outputs Z0, Z0, and Z1 is going to be matching the current state. So whatever you have in the state is going to be in the output. Now, from this table, what we are going to do is we will find the equations for our 2 flip-flops. You can see in red, you can, since we have 4 variables, x0, x1, y0, and y1, we will have 4 by 4 kernel map. And we copied these, since we make the assignment to match the K-map here and here, we just copy it. We just copy the table, 1, 0, don't care 0, 1, 0, don't care 0, and so on. You copy this here, and you copy this red column here, and this one here, to get dy1. And the black ones, you copy them here to get dy0. From the kernel map, or from K-map optimization, you will find that you have 4 boxes. Notice that we make use of the don't cares. And those 3 boxes here is going to be represented by 3 terms. This will have 2 variables. This one will have 3 variables, and this one will have 3 variables, as you can see. dy0 will have 3 boxes or 3 rectangles, and you will have this one with 2 variables. This is the 2 variables, and those 2 with 3 variables. I'll pick one of them just to make sure. Let me pick 2 of them. I'll pick this one and this one. To get this one, this is going to be y0 and x0. So it's y0 and x0. For this one, it's going to be y0 bar, y1 bar, and x0. y0 bar, y1 bar, and x0. Now, after describing this example, and we got the equations, those 2 equations, we will generate the block diagram. This is the block diagram. We have 2 flip-flops, y0 and y1. And we say that the next state for y1 is this one. It has 3 terms altogether. And for dy0, it has 3 terms altogether. And we get the terms, and you can check them here. Notice that we have 2 inputs. So to understand what's going on here, you will have at the beginning a reset. You will reset both flip-flops. So the current sum would be 0, 0. And whatever you get here in the input, you will add it to the sum, and you will calculate, the circuit will calculate for you modulo 3. So for example, if you have 0, 0, and you have the x0 being the least significant, 1 here and 0 here, then after you give a clock, a full clock like this to the clock, the result that will be inside the flip-flop is going to be 1, and this 0 will stay the same, 0, because you will add them together. Notice that the outputs, since this is more model, the outputs are exactly the same as the states. At this point, we will move to the other flip-flop types. Now, we described how to design from the specification all the way to the block diagram using D flip-flops. We will have different flip-flop types, being the JK flip-flop and the T flip-flop. We will describe them, and we will give an example that shows the design using one of them. So the basic descriptor for understanding and using different flip-flop types, we need to know the characteristic table, the characteristic equation that we derive from the characteristic table, and also the excitation tables. We will define them, and we will show those 3 descriptors for each flip-flop type. In JK flip-flop type and the T flip-flop type, we will explain its behavior and how to implement them using what we know from previous classes. Now, the characteristic table defines the next state of the flip-flops in terms of the flip-flop inputs and the current states. So you try to get the next state knowing the inputs and the current states. The characteristic equation defines the next states of the flip-flop as the Boolean function of the flip-flop inputs and the current states. So the characteristic equation is actually matching the characteristic table, but the representation is different. This is a table, and this one is an equation. Now, those 2, being the characteristic descriptor, is used in analysis. When you already, for example, having the block diagram, you know the sequential circuit, and you try to analyze it. In design, which is important to us in this chapter, we use the excitation table. The excitation table defines the flip-flop input values as a function of the current states and the next state. So given the current states and the next states, I want to know what let me share again. So now we know the characteristic table, the characteristic equation, and also the excitation table. The major difference, those two, we use them in the analysis, and this one, we use it in the design. Now let's see those descriptors for each flip-flop types. We will start by the SR flip-flop descriptor, which we already know. The sample for the SR flip-flop, you know that this is a flip-flop because of this one. This is the clock, and you have the SR inputs, and you generate the Q and the Q bar. Now, the characteristic table for the SR, since it's an S and R, not S bar R bar, there is no bars here. Since it is in a normal form, both of them will be active high, meaning if the reset is 1, you will reset. The next state would be 0, so you will reset. If S is equal to 1, then you will set. The SR, when they are equal to 1, this is the forbidden case. It will give you undefined value. When they are 0 and 0, the next state would be the current state. So there is no change, and here you are saving the value. You are saving the value. Now, the characteristic equation for the SR latch it's written in a different way than the normal way that we use the truth table, and you find the one and you try to find what's the combination of the inputs. You understand it this way. The next state going to be 1 when you are sitting, or it would be Q if you are not resetting. And to get rid of the problem of the 1, the forbidden case, you would say if S is equal to 1 and R is equal to 1, then the next state is going to be 0. This is the way you write the characteristic equation for the SR flip-flop, and there are other ways as well, but the SR flip-flop is not that important in design. Usually we design using D flip-flop or JK flip-flop or T flip-flops. So we are not gonna give it more time. The excitation table now is actually the same as the characteristic table, but it's written in a different way. You can notice here that we try in case you know the present state Q of T and Q of T plus 1, which is the next state. So the excitation table is knowing that the current state Q of T is this way, and the next state Q of T plus 1 is this way. What are the inputs that give us this combination? Let's take the first case. If you have Q of T equal to 0, and the next state is also equal to 0, this happens if you are resetting. So the R is equal to 1, and the S is equal to 0. If you reset, the next state is going to be 0. Also, this happens if you have S is equal to 0 and R is equal to 0, meaning there is no change. And knowing that we started from the present state 0, the next state won't have any change, and it will be kept as 0. So those two cases will give us this combination going from 0 to 0. And it could be written in the excitation table as 0 and X. So it means that S must be 0 and the R could be 0 or 1 or simply don't care. For this combination, the present state is 0 and the next state is 1. This happens only when you try to set. When you try to set the next state, then S is going to be 1 and the R is going to be 0. Similarly, for this case, the next state would be 0 if you start from 1 and the next state going to 0, then you must reset. The R must be 1 and the S must be 0. The last case, which is 1 and 1, this happens similar to what we studied or what we checked in the first row. 1 and 1 happens if you are setting, so the S is 1 and the R is going to be 0. If you set, then the output here is going to be 1. Similarly, it's going to, the next state would be 1 if you start from 1 and you keep no change. So you'll end up with 1. And this happens when you have 0, 0 in the S and R. This means that it's a combination of S being a don't care value and the R must be 0. This is the excitation table, and we would see a full example later using one of the types to check how the excitation table help us in the design. For the D flip-flop, it's the easiest type. The characteristic table is simple. Whenever you have a D, the next state is going to be the same. The operation is reset and set, but it's not important to say it for the D flip-flop. The characteristic equation, the next state is going to equal to the D, and this is the symbol, as you can see. We take the S and R out and we replace them by a symbol D. Now you can see that the excitation table, we just flip those columns, but the meaning is different. The excitation table says that if we know that the next state is going to be 0, then the D flip-flop input we must put 0. If we want the next state to be 1, then the D is going to be 1. For the JK flip-flop, which is the first new flip-flop type, it's behaving as the same as the SR flip-flop. And this is actually why we presented at the beginning. Except that the forbidden case 1, 1 is no longer forbidden when the J and K is equal to 1. It is allowed. This is matching, the J is matching the S and the K is matching the R now. If they are equal to 1, 1, it is allowed, and the result is actually the flipping of the bits, or we getting the opposite state. To understand this, first the sample is J and K. Instead of S and R, we take the J and K and we put S instead, S and R. Instead of S and R, we put J and K. This is the sample. Now, the characteristic table, it tells you if you used JK 0, 0, there is no change. 0 and 1, this is the reset. 1 and 0, this is the set. This is up to this point, it's the same as the SR latch. The change is here. Now, 1 and 1 is allowed, and it's going to generate the complement of the current state. So the next state going to be the complement of the current state. Now, for the characteristic equation, you could see that the next state Q of T plus 1 is either J Q bar or K bar Q. And this is easily translated into the implementation of the JK flip-flop. You could implement the JK flip-flop using a D flip-flop by implementing this function, the J with the Q bar and the K bar with the Q. Now, we move to the excitation table. Now, the excitation tables, we are trying to, in the excitation table, we're trying to find the J and the K values, given that you are in the current, a specific current state going to another next state. So if you are going from 0 to 0, then we will do similar analysis that we did in the SR, and you will end up with 0x. Same thing for here. In 1, 1, you will end up with x0. Let's match it with the SR. Going back to SR, this is the same thing. This is 0x, and this is x0. Now, for the other two, since we are allowing this value, which is, or this row, it's no longer forbidden to have j is equal to 1 and k is equal to 1, then to have 0 and 1, either you would set, so j and k value is going to be 1 and 0. So either you are setting the value, and because of this, the next stage is going to be 1, or you are complementing. If the present state is 0, and then you complement it to 1, they will give you the same result, and this will be translated to 1 and x. You can do the same thing here, and you will find that it's x and 1. Now, you can derive actually the characteristic equation from the excitation table, because the excitation table actually helps us with the design. And if you don't know the characteristic equation, then this will help you to find it. The characteristic equation for the JK, you try to find what's going to give you 1 in the next state, which is this and this. And this happens if you have Q bar and J, or you have Q and K bar, which matches the characteristic equation. Now, the next flip-flop type is the T flip-flop. And the T flip-flop, instead of having the J and K, we have only T. We have only T. What happens here, the characteristic table, it tells you that if T is equal 0, then the next state is going to be exactly the current state. If the T is equal to 1, what you do is you're going to complement, which means that the next state is going to be the complement of the current state. The excitation table is going to be the opposite, as you can see. Now, what's the behavior of the T flip-flop? It has a single input. If the T is equal to 0, no change. If T is equal to 1, then you flip. You flip, meaning that you change to the opposite state. It's actually the same as the JK flip-flop, with J is equal to K is equal to T. And you need a reset, actually, in all the flip-flops to make sure that you start from 0 and 0. Now, to get the characteristics equation, it's actually T XOR with the Q to get the same behavior. Because if you want T, if T is equal to 0, then Q of T is going to have only Q. If T is equal to 1, then 1 XOR Q will generate for you Q bar, and Q of T plus 1 is going to be equal to Q bar. So the characteristic equation is simply the input T XOR what's stored inside the flip-flop, which is the Q. To implement it using D flip-flops, you use an XOR gate with the first input T, and the second input, the feedback going back from Q. We will check the same behavior, but now we will look at it from the timing diagram point of view. We use the characteristic tables to find the output waveforms for the flip-flops. Here we will check the D and T, and you will see the difference. Assuming that you have a clock here, and this clock, or all the flip-flop types, are rising edges. So in the rising edges, you will check what happens, or what is the input, and based on the input on the input, you will try to figure out the output. You would see that the output is, for the D, is this output waveform. Notice that there is a certain delay from here to here. So at the rising edge, you check the input. The input was 1, so you keep it as 1. Previously, we start from 0, from the reset point. And then this is going to be 1. You will check it again in the rising edge. You found that the D is going to be or equals to 0, so you go down and you keep having it low until the next rising. In the next rising, the input D is 1. You bring it back to 1. And at the end, in this rising, the input was 0. So after a certain delay, you have the output 0. The delays are shown here, here, and here, and here. This is the delay of the flip-flop, and if there is any other associated gates. For the T flip-flop, either you keep the same value or you flip. Either you keep the same value or you flip. So what happens in the T flip-flop is same thing. We look at only the rising and we try to check the output based on those times. And the first rising here, at this point, you have the value of the T. We will assume that this is T now, is 1. And since it's 1, you will flip. It was 0 before, and then you will flip it to 1. At this point, the T is 0, so you don't flip, you keep it the same. So you keep the output the same. And this rising, the T value is 1, so you flip back. And at this point, the value of the T is 0, so you keep it the same. You keep it the same. You keep it the same here and here because the T value is equal to 0. Here and here, since T is 1, you flip. It was 0 and then it goes to 1. It was 1, it goes back to 0. So you can see the relation between the D and T here. Both of them have only a single input, but the behavior is different. In the D, you pass the value. In the T, either you keep the old value or you flip it. Now, we will check the same behavior now, but for the SR latch, SR flip-flop and the JK flip-flop. We check the rising for the change from low to high. For the SNR, if we try to get this output form, we consider these to be an SNR. If you are in an SNR, if you have 1 and 0, then you must be sitting. So the output is going to be 1. If you have at this point S is 0 and R is 1, then you are resetting. If at this point you have them as 1, the S is 1 and R is 1, this is the forbidden case. And at this point, you have no idea what's going to be the output. And for the last case here, we have S equal to 0 and R is equal to 1.
So we reset again, and we make this value to be, the output value go to be 0. You can see that this is not desired, and because of the possibility that this might happen, nobody use SR in the design. Now, the JK flip-flop, in the JK flip-flop, now these two inputs are J and K. You would have the value 1 and 0, which will match what's the SR. Similarly here, if it is 0 and 1, it will reset. Now here, we have 1 and 1, and when the rising edge happens and you have S equal to 1, we have J equal to 1 and K equal to 1, then you will flip. Whatever value you have here, you will flip it. It was 0, you'll flip it and make it 1. And then after this point, you have a reset. And because you have a reset, you will go to 0. This is the output waveform for all the flip-flop types given a certain input waveforms. Now, at the end, we will have an example, a design example of the binary up-down counter with an enable E. We will design this. We actually have the choice to design this using D flip-flop, T flip-flop, or JK flip-flop. In this example, I'm designing using JK flip-flop. So a design choice is to use 2 JK flip-flops, A and B, and we will use 2 inputs. Those 2 inputs being the enable E and the count forward F. If the enable is equal to 0, the circuit remains the same. It doesn't count up nor down, regardless of the value of F. If the enable is 1, this gives the F its functionality. When F is equal to 1, the circuit counts up. So it counts up like this. If you start from 0, you count up 1, and then 2, and then 3, and then you go back to 0. If F is equal to 0, then the circuit counts down this way. If you start from 0, you'll count down to 3, and then 2, and then 1, and then go back to 0. This is the specification of the problem. And based on the specification, we came up with this state diagram. Either you will count up this way. This is counting up. If you have the enable, this is the enable equals to 1. And you have F equal to 1. So you will go forward, starting from 0, 1, 2, and 3. You will count backward this way. Let me change the color. Starting from 0, you go to 3. If the enable is 1, but the F is equal to 0. F equal to 0 means that it is not forward, so it must be backward. So you go 3, 2, and then 1, and then at the end, 0. Now, if the enable is 0, this is all the other cases where the input, where the state goes to itself. And this happens when the enable is equal to 0. You don't look at the other input, F, at all. You stay at the same state. Now, from this state diagram, we fill the state table. Note that the state table is having inputs E and F, present state A and B. We have 2 bits or 2 flip-flops in the present states because we are counting up to 3, starting from 0 up to 3. So we have 0, 1, 2, and 3, and then we will go back to 0.
And we know that we need 4 states this way. And since we know we have 4 states, we need 2 bits to state assign these 4 states. We make the first one 0, 0, the second one is 1, 0, and then you have 0, 1, and 1, 1. And you fill up the table by having those 2 bits for the present state and for the next state. Now, let me write this line here. What you do in this side of the table, you fill up this table first by filling the inputs 0, 1, 0, 1, 0, 1, 0, 1, and so on. The A 0, 0, 1, 1, and so on. F 4 zeros and 4 ones, 4 zeros and 4 1, and the E is 8 zeros and 8 ones. This is fairly easy and you can fill it quickly. Now the question, look at the how to find the next state. This is the question. And you look at the state diagram to find this by checking what's the present state. If the present state is 0 and the input is 0, 0, it means that you will go back to the same state, which will be 0, 0. Now, if you are in 0 and 1, which is this state, and the inputs are 0, 0, then you go back to the same state. You notice that whenever the enable is 0, you will stay at the same states. Whatever the state you are in, you will stay in the same states. Now, when the enable is 1, and you are counting up, meaning that the F is equal to 1. If you are in 0, you will count up to 1. If you are in 1, you will count up to 2. If you are in 2, you will count up to 3. If you are in 3, you will count up and round back, so you will go to 0. And those remaining cases, when the enable is 1 and the F is 0, you will count down. From 0, you will go to 3. From 1, you will count down to 0. From 2, you will count down to 1. And from 3, you'll count down to 2. Now, we got the state table. What will happen now is we will use the excitation table of the JK flip-flop. That will help me finding the remaining columns to help me design the circuit. We will go back to the excitation table of the JK flip-flop. This is the excitation table, 0, 1, 0, 1, 0, 0, 1, 1, and the J 0, 1, XX, K, XX, 1, 0. So I will try to write it here. So this is, if you have Q of T and Q of T plus 1, if it is 0, 1, 0, 1, 0, 0, 1, 1, now the value of J and the value of K in the excitation table, if you forget them, you could derive them or just try to memorize them. The J and K, to go back again, the J is 0, 1, XX. Zero, 1, XX. The K is XX, 1, 0, XX, 1, 0. So now we check the present state with the next state. If you want to go from 0 to 0, what will happen to the J and the K? Now, as you can notice here, we have the JK for the A and the JK for the B. So let's consider A only, meaning that we will consider
the column A in the present state going to the column A of the next state. So from 0, 0, going back here and checking from 0 to 0, it's the J going to be 0 and the K going to be X. So we write down 0 and X. From 0 to 0, 0 and X. From 1 to 1, from 1 to 1, it's going to be X and 0. From 1 to 1, it's going to be X and 0. Similarly here, X and 0. From 0 to 0, this is 0x, 0 to 0, 0x. From 1 to 1, x 0. From 1 to 1, x and 0. From 0 to 1, that's from 0 to 1, it's going to be 1x. This is why we have 1x here. And you continue filling the value of J, A, and Ka. You do the similar scenario for J, K for the B. Let me do it for this part. Let me do it for this part down in the table here. So I want to find the JK of B. I look at the column of B's. From 0 to 1 is going to be 1x. From 0 to 1, 1x. I fill 1x here. From 1 to 0, from 1 to 0 is going to be x and 1. This is x and 1. From 0 to 1, from 0 to 1 is 1 and x. And from 1 to 0, it's the same as this one, from x and 1. You can see that the excitation table help us filling the part, the second part of the table. And this part is the one that we are going to use in the optimization. So what we do is we take this part here in the right side of the table, and we will try to get J, A, and K, A. This is J, A, and K, A. By using the Carnot map, you fill this one in the K map. It has 4 variables because these are the inputs. B and A, this is B and A, F and E, this is F and E. And you fill it as you can see, looking at this column. You fill it as 0, 0, X, X, 0, 0, X, X, 1, 0, X and X, notice the jump, 0, 1, and then X and X. You can see that the don't care here is helping out, helping a lot in optimization. You fill also the K of A in the table, in the Carnot map over here, and you can see that we can take those two together and those two together to generate the terms where you have 1 in the K map. You get from this one, it's going to be E, F, and B. And from those two, it's going to be E, F bar, and B bar. You can take also the E as a common factor, and you end up with FB or F bar, B bar. And if you are careful, you notice that this is a NOR gate. Similarly, for this one, you will get the same equation. This doesn't happen all the time, but for this case, it is the case. It's having the same equation for the JA and the KA, because you can see that we got those together and the one was here, and we got those two together, but the one was in here. So the don't care even help us in optimization and having the same result for the JA and KA. For the GB, the JB and KB, it's even easier. We generated one box here and another box over here. And this one is only E. You can see E is the only one that is constant. So we have JB equal to E and also KB equal to E. And you can follow how did we do the optimization? And from those 4 equations that we generated, I will write them down again here. This is JA and KA, they have the same function. The JB and KB, they have also the same function. We use now a JK flip-flop. And you can see that if you have A, this is A, and this one, the JK flip-flop for B. For A, the next state function for the J and the K are the same, which are the XNOR of E and the XNOR of F and B, ANDed with the enable E. For the part of B, it's just simply the enable going to the J and the K. And if you have this circuit to verify its operation, you have the clock here, and possibly you have a reset input as well to reset from the beginning 0 and 0. And then if you have the enable equal to 0, it doesn't count up or down. The value here is going to be 0 and 0 all the time. So at the beginning, let's say that you reset and you have the 2 flip-flop as 0 and 0. The enable was 0. If you change the F from 0 to 1, and you give a clock signal, let's say you give 1 clock, you won't see any change because the enable is 0. Now, if you move the enable also to 0, now the enable is 1 and the F is 1, which means that this circuit will count up. If you give it another clock, then the B being the least significant, I think the B was the B was the least significant. I have to make sure of this. Then the value here would be counting up, so it will change to 1, and this will be the same. It will keep the same as 0. If you give it another clock with the same input not changing, it will count up again, and it makes it, this is 1 and this is 0. And if you give it another clock, it will be 1 and 1, so it's counting up. If at this point you change the enable back to 0, then you have the enable 0, and this will be the same value in the JK flip-flops, even if you give it many clocks. And so on. This way you can verify the design. And now you know how to design circuits, sequential circuits in general, and you have tools to help you design the sequential circuits, like the state diagram, the state table, and you have different types of flip-flops, like the D flip-flop and JK flip-flop, and also T flip-flop. As an exercise for you, you can design the same circuit, which is the binary up-down counter with enable using D flip-flop. You will notice that the circuit is slightly larger. And that's one of the advantages of using the JK flip-flops.